Hi everyone, in this video we'll be programming a PIC10F series microcontroller and just do a simple blinky project. We're just going to blink an LED. So here's a couple of things we need. We need a breadboard. Here I have PIC10F220 PIC microcontroller and a 5mm LED and 220 ohm resistor and PIC3 for programming and some jumper cables. So you will also need a screwdriver like this just to pop this into the breadboard. Like if you want to remove it, it's very easy to get it underneath the chip and just remove it without bending the pins on it. The breadboard, yeah, this one I had it around for a while. Just I've seen better days. There was like a positive rail here, which just diminished over time. I guess UV and maybe it stayed a bit next to the window. If you want to get one, try not to get the cheapest one because these contacts and everything could be really problematic, and like just the labels and the markings they will wear off. So just try to get a mid-range one. It's really hard to get wrong with these ones, but yeah, just don't go for the dirt cheap ones. You can get smaller ones like this for smaller projects, all good. The pick I have here is 10F220. It's baseline series. Not sure if you can see it on the camera. Oh yeah, almost there. Yep. But you have to make sure the part number is correct. These baseline chips, the programmer has no way of telling whether the chip is correct or not, so you will have all sorts of issues. LED, you can get pretty much any, low power LEDs like this. It's all fine for this project. And the resistor is just going to be like a current limiting resistor because the PIC chip can only source or sink 20 milliamps per pin. And we just want to limit the current. We don't, because if you draw more than that, the best case, your program will stop running. In the worst case, either your PIC will just die or just the LED will just blow. So we don't want that. We want a current limiting resistor there. So and we have here PIC3. It has well, it's not the best programmer out there, but it works. I had this for ages and it just works. So the most recent one is PIC4. If you don't have a programmer, don't buy PIC3, go buy PIC4. I haven't used it myself, but I imagine it just supports more newer PICs. So yeah, but if you have a PIC lying around, also fine because it works. There's nothing inherently wrong with it. And we need a bunch of jumper cables. Well, we'll just use them to basically wire up our chip to the programmer, and then perhaps some to wire up the ground the LED or maybe some other stuff. Optionally, you might also need a cap, like a small cap, right? In this project, it doesn't matter, but if you have like a 0.1 micro or 1 microfarad cap, that would work real well, especially if you're gonna do some analog digital conversions with this chip. Then you need the bypass cap. You have to have it. In this project, I'm just gonna lay it out because it's just gonna work. But if you want to get serious, especially the analog stuff, you need to have one or more caps there. Don't put something too big, because if you put something like 100 microfarads, then the PIC might have problems powering the circuit because it's gonna cause an inrush current, and it might trip some of the internal circuit of PIC, and it will think that there's a short, and it just won't power your circuit. Okay, so before jumping into our circuit, let's have a look at the data sheet. There we go. It's the data sheet for PIC220 and 222. They are both very similar devices, except 222 one has a little bit of more memory. So the PIC data sheets are quite well structured, and they're almost always the same. especially with these, baseline 8-bit series. Just talks about the CPU a little bit, special microcontroller features, peripheral features, and low power features. So this is a baseline PIC. PIC here stands for Peripheral Interface Controller. 10 as a series of it. F is flash programmable, so we can program it as much as we want. Well, there's actually 100,000 times. There is also C series, which you can only program once. But we don't want that because when you're doing hobby projects as far as you are doing prototyping, yeah, you just want to, but in production, perhaps you can go with a C bit, especially from a cost point of view. This is a baseline pick, meaning it's absolutely bottom of the line. Pretty much all of the other picks out there has better features, more memory, more pins. But for simple applications and like simple sensor applications, transmitters, receivers, there's still countless projects you can do with this one. It's a wide operating voltage range, which many of the modern PICs do, but this one also has it. So you can just power it from 2 volts. Can provide that, but just simply 2 batteries and in series, and that would be enough to run the PIC. It has 4 I/O pins. It has a timer, 8-bit timer in it. You might perhaps, once we are done with the blinky project, we can just use the timer to dim the lid a little bit. And it has an analog digital converter. It's 8-bit. So it also has, what I like about it, is an internal reference channel, which is a fixed 0.6 volts, I guess, and that can be used to measure the supply voltage. If you're powering it by batteries, you can just guess, like you can just estimate whether the batteries are empty or full, like depending on the chemistry that you use there. It's also like it will reduce the noise, like without a help of an external regulator or reference, you would be making better conversions, analog conversions to digital. There's a whole bunch of other features. We're not gonna get into depth in here, but let's scroll down a little bit to see the pin diagrams. So what we have here is a DIP package, nice and easy to work on a breadboard, and this is the pin diagram. Now let's start populating our breadboard. We're gonna take our PIC and pop it in there. So one problem that you might have here is this PIC has been around for a while. I have been playing with this particular chip for a while, so it's okay. We'll just get into the breadboard. But once you buy a brand new one, the pins, the gap here will be a little bit too big to fit on there. And if that's the case, you can just, roll it a little bit, just give it a little push gently, like all the pins, right? Just a little bit to close the gap and so that it will fit in. Or you can just align it to the holes on the breadboard, and then like from both sides you can just squeeze it a little bit. This is not very problematic because it's just only 8 pins, but if you have a longer chip, then you might need to just go through all of the pins section by section to just get them like fit and close the gap, and so it will fit into the breadboard. So once all the pins are in there, we'll just kind of push it gently and it will go in there. But if you want to remove it, that's another problem, because if you try to pull it out, you might accidentally damage the pins. So that's why you will need a screwdriver. So there's a gap in the middle of the breadboard. You can just put this is like a very small, field variety flathead screwdriver. You'll just put this in the bottom of the chip and in the gap in the middle of the breadboard, and pull it like upwards from one side. Don't go all the way because that will bend the pins, and then you can just put it in there from the other side and just lift it up a little bit more from here, a little bit more from here again. So this way, yeah, we can just done, pop it out. So this was too easy, but if you buy a brand new dip package chip, you will see what I mean. So now I'm gonna pop it back there again, and now, okay, it's nicely fit there. Now we need to connect our PIC kit to the chip. So the first pin, the first pin on our PIC kit that's marked by an arrow is the MCLR, that's the master clear and the reset pin. So the MCLR goes to, as you can see on the diagram, on the first pin, pin number 8, like the pins numbered like this: 1, 2, 3, 4, 5, 6, 7, 8. So you can see in the datasheet. So MCLR goes to pin number 8 in this PIC. And also, like, just put it away from the PIC, so if you need to get in there with a multimeter and measure some stuff, so it will give us some space. The second one is the power supply, which is going to be our voltage supply in this case, but I'm not going to connect it yet. First I will connect the ground, because the next one is the ground, and it's generally good practice. Just connect the ground first. So I left one pin there. This is the ground, black color, and that ground goes to right under the MCLR pin, which is pin 7 on the datasheet. Now let's connect our power, the VDD. This is like FET based chips, so they call it DDD. That DD stands for drain. Okay, there you go. Well, if it stands for something else, let me know in the comments, because yeah, that's kind of, you know, the things you kind of know it, but I'm not sure about my source. Okay, what else? We connected the reset, power, ground. Okay, now we need to connect the data and the clock. So just pick green as the data and yellow as the clock. So I'm just going to put them in the correct order here. The first one is data, the next one is clock. There you go. And we connect data to the 5th pin. Okay. Yep. And the clock is on the other side. There we go. Okay. So at this stage, it's generally a good idea just to go through your connections and make sure they're all correct. Go through the data sheet of the PIC chip you have. Go through the pin diagram of the PIC kit if you're not sure, and yeah, just give it a quick check. And now the last pin, the what is it? The 5th pin is also called GP0. So unlike other baseline PICs like 16Fs, these ones they don't have ports, they have these GPIO stuff. So, and GP0 seems to happen one of those pins that we can control through our program. So I'm just going to pop our resistor in there. Okay. And then put our LED. Okay. Now this LED, so we'll turn it on, we will turn the pin on. The current will go through, in a traditional sense, will go through the resistor, it will go through the LED, and well, it needs to go through somewhere, right? So you just connect it back to the ground from here. So I remember that this black one was the ground, so we're just gonna connect it there. So I just skipped a bunch of breadboard basics, but as you might have imagined, all the horizontal slots are connected. The vertical ones are not, obviously. Okay, so the problem here is not exactly a problem, but one thing that is usually skipped is, so let's say your VDD, this is a wide operating range chip. So let's say our VDD is 5 volts in this case. And once you turn this pin on, you won't be seeing 5 volts here because there's some internal circuitry, and it will drop 0.7 volts. That's in the data sheet. It's the voltage drop on the pins. So you will get 4.3 volts here. That's something to note. When it's like it's enough to turn on this LED, that's fine. But if you want to power this with 2 batteries or like 2.0 volts, then it might not be enough to turn on some kinds of LEDs. We are not going to get into this, but you need to know the forward voltage of your LED, like what's the minimum voltage that it needs to turn on. Then the PIC has to be able to supply that. So we can do another trick, like if your VDD is enough to turn it on, we can just flip it over, and instead of driving it high, we can drive it low. So instead of connecting to the ground, we can connect it to the VDD, and then we can use the pin as a sink. We can use the pin as a ground, but for this one, we'll keep it simple. So the LED will turn on, we'll power everything through the PIC kit. So it's all good. Now we have built our circuit. There's the PIC chip, there's the VDD voltage source, you have the clock, data, ground, and also ground connected to the LED, MCLR, all of them are connected. Now the last bit you can do is to add a cap to the power source. So just to reject the ripple on the VDD. For this application, it's not necessary, but in your designs, it's generally, especially if you're dealing with analog stuff, you need to definitely put some cap on the between the VDD and VSS, so like between the power and the ground, just to reject the ripple and get clear analog readings. So now I think we can connect that one anyways, just from VDD to ground rail. This ground rail is not connected to anywhere though, but we're just gonna connect that with this jumper from here to the ground. So on the breadboard, like in the middle part, yeah, it's like nothing is connected vertically, it's all horizontally connected. So that's why just, the power is coming here, the power is going there, we know that. But on the power rails, it's just vertical. Okay, so the ground rail is this one, the power rail is this one, which I haven't connected, but I know that all of these are connected together. Okay, so without further ado, let's start coding. We have MPLAB X IDE here. It's from Microchip. It's integrated development environment for all kinds of PICs and Atmel microcontrollers from Microchip. There's really a lot it can do, lots of tools. Could be a little bit daunting for beginners because there's a lot going on, and it's built on the NetBeans platform, which hasn't aged quite well, especially in the UI sense. But it's a pretty powerful tool, and once you get used to it, it's also easy to use. So we're just going to create a new project, Microchip standalone project. I'm gonna pick our family, which is baseline 8-bit MCU. Here we're just picking our semiconductor make and model. It's PIC10F220 in our case, and the tool is the programming tool. We're just gonna pick PIC-it. So PIC-it is already connected through USB at this stage. You can see its lights on. But you just want to connect the USB connection is a bit tricky. PIC-it 3 is plagued by all sorts of problems, especially while powering the circuit. So you might want to connect it directly to a PC rather than using hubs or anything like that. We're gonna get into that. I hope we don't run into any problems, but if we do, it's going to be a good learning practice as well. So yeah, we picked the PIC-it, our chip model, and yeah, family, all good. And debug header, yeah, we don't use any debug header for this project. And these baseline ones, well, the midline ones you can debug with PIC-it, but the baseline ones needs a separate debug header, which we don't have and we don't need for this project. And the compiler. So when you install MPLAB X IDE, it just doesn't come with a compiler. You have to install a C compiler, in this case XC8 from Microchip. I installed. There's a free and a paid version. The paid version is well above the budget of prototyping and hobbyist level projects. But if you're going for some, I don't know, commercial large scale projects, should be fine. But the free version is just a little bit less optimized when it's building the assembling the code. So if you have some issues fitting the code into the chip, then it's probably a better idea for prototyping projects to go for a chip with a larger memory. Or like just go a little bit to 16F series or 18F series or something like that. That's gonna be cheaper. Okay, you pick XC8. Again, the installation of it is pretty straightforward, just as MPLAB X80. And I have installed all of these on Fedora operating system with absolute zero issues. Just follow the instructions, next, and it was all good. But let me know down below in the comments if you have any issues installing these. The project name, yeah, just put a long boring name here. blinky10F220. So we know what we're doing. The name is quite descriptive of, okay, this is a blinky project. Yeah, it's a blinking LED, which series. Good. Yeah, finish it. Okay, we have the project now. This is dashboard, which is going to be quite handy once we start coding. Just need to create a source file now. New main.c. That's entry point for our programs. This is pretty much textbook C development happening here. Okay, now before we start coding, we just need to add some configuration directives for our chip here. It's quite easy to do. There's a very handy tool for that. Go to Window, target memory views, and configuration bits. That's the first thing that you want to do. So I'm just going to talk briefly about what these are. One of them is the internal oscillator frequency. So this PIC, the 10F series, doesn't support an external oscillator. It has like all the internal 4 MHz and 8 MHz option. If you're not sure, just go with the lower one because the power consumption will be less in lower frequencies. And if you need your processor to be faster, then you can just go for the higher options. MCLR pull-up pins, at this point it's not important because we're not going to be using that. And I'm going to leave the watchdog timer enabled. Watchdog timer is an internal module in the PIC that runs in parallel. That's independent of your program, and it's basically it's basically expecting a ping of some sort from your program, and if it doesn't get it, it's just going to reset the microprocessor. So it's generally good practice to keep it on. So if something goes wrong within your code or somehow the program execution gets disrupted and your controller is stuck in an awkward state, the watchdog timer will just reset it and everything will be jolly fine. So I'm just going to keep it on and we will just show how to clear the watchdog timer in code. We don't need code protection at this stage, and the rest one is a reset pin. It needs to be, so yeah, we will set it as digital I/O. If you don't set it as digital I/O, you have to connect it to VDD with a resistor, so your processor is not in reset state. You can hook up a button there that pulls it back to ground. You can use it as a reset button as well, but in this project, we're just going to keep the components to a minimum, so we're just going to use it as a digital I/O. So we don't need to, it's not going to be in reset state. The micro will just run. Changing these values here doesn't do anything actually, so we have to generate the source code to output and generate some code. That's going to include XCH here, that's the XC compiler header file, and it's here too. So the expectation for us is to copy and paste all of that code and put it right at the beginning of our program, just before everything. So I'm going to remove this so we don't want to double it. There we go. The configuration is here and we include the XCH file. So that's all good. Now, you don't need this return statement here. That will just end our program. First, we need to set this set our pin. That's the GP0 in this case, or general purpose IO pin. But it's also, is you see in the data sheet, it's also A and 0. That's also an analog pin. And by default, these pins are set up as, I don't know if there's an exception to this, but on all the PICs that I have played with so far, they are all analog inputs by default. So we have to set it to digital first. It's quite simple. You just put AN, control space, and MPLab will give us some of the definitions that we can use, some of the templates that we can use. That's quite handy, and we will clear this bit. That means that AN0 is not an analog pin, it's digital. Now the next thing we need to do is to set it as output. So for that, we're just going to hit the twist bits. We don't have bits for it, we have the entire twist GPIO, so let's you can write any byte here. If we write 0 to here, if we clear this twist GPIO, then all the bits, all the pins, GP0, 1, 2, all of them will be outputs. The exception to this is the MCLR pin, but we're not going to get into that. Okay, so now we set our GP0 as output. We just need to create a loop here, right? And in this loop, we will set our GP0 to the opposite of whatever it is. So we'll be toggling it. If it's 0, it will be 1. If it's 1, it will be 0. And we'll just add some delay here. For that, we will use the delay function. Delay ms. We have the ns as well for nanosecond delays. And we also need to, this stage, clear the watchdog timer. Okay. So yeah, I don't know if 1 second will be enough to clear the watchdog timer, but you can just go and have a look at the data sheet quickly. Should be under special features, watchdog timer. Let's see. Okay, maybe we should try reading this. Period is a nominal timeout period of 18 milliseconds. Okay, so that's not enough. So in this case, watchdog timer will reset our PIC. We don't want that because we will be doing nothing for 1000 milliseconds. You can change this with a prescaler. Yeah, 2.3 seconds. Okay, you can try doing that, or just to keep things simple, you can just turn the watchdog timer off. But in the next video, perhaps we can get into that, keep it on, change the period of it, but let's keep it off for now. Okay, so we have the configuration. We're setting our pin as a digital output, digital end output, and we're toggling it, and we are waiting 1000 milliseconds and 1 second as well. So the next thing that we need to do is to power up our circuit from the PIC kit. To do that, just right click on the project, go to properties, and select PIC kit, and under configuration, and select power. And we're just going to take power target circuit from PIC kit 3. Now the voltage level selection is a bit tricky. For the baseline PICs, you just want to stick between 4.5 and 5 volts. Because even though the PIC can function in lower voltages, unless it has an LF part name in LF in its part name, it still needs that to be at 4.5 volts minimum while it's being programmed. So, and 5 volts is quite tricky because with the modern USB devices, they rarely get to 5 volts. You can get something like 4.9, 4.8, and that will trick the pickets to think that there's something wrong with the power line, will refuse to program your chip. So what you want to do in this case with these baseline picks is to stick to something that's above 4.5 volts. I'm just going to pick 4.6. It doesn't matter, it could be 4.7. Just try it with your different USB ports and all that. The general idea, just hook it up straight to your computer. If you're using hubs or peripherals like keyboards, monitors, things can vary really a lot, and that will ruin your day. So I'm just going to pick 4.75 for now. That's good enough. Apply it. Okay. Now clear this output. Okay, now we're just going to make and program the device. That's it. Oh, build failed. All right. Yeah, for the delay to work, we need to define this external frequency template. So I'm just going to copy this and define it right above the inclusion of XC header. In our case, our frequency is 4 megahertz. So that's why I just need to define it in hertz. It's 4 million hertz. Okay, let's try again. Yeah, it's connected. It's asking us about the powering it. It's okay in this case. Yeah, it's being powered. And it's done. And there we go. Well, with every blink, the camera is slightly running out of focus, but that's pretty good. We might have a couple of issues here, especially with power, and the error messages are absolute rubbish. It could fail at the verify stage or at the power circuits. If that's the case, just try different voltages between 4.5 and 5 volts, and try different USB ports on your computer. That's the most problematic issue with PIC10F220 and the baseline chips. But it's very unlikely that there's something wrong with your. Just check your connections just to be sure. But these are very robust chips, and it's very unlikely that you brick them or you brick your PIC10F220. There's all protected and they have clamping diodes and everything. It's almost always a USB powering issue. And if you're in doubt, just use an external power supply as well. That's just to clear things. And that's pretty much all. I hope you like my video. Please like and subscribe and comment down below if you have any suggestions, questions. More than happy to answer. Thanks again. Bye.